Welcome to August Leetcode Challenge. Today's problem is largest component size of common factor. Given a non-empty array of positive integers, consider the following graph. There are A-length nodes, labeled a to 0 to the A-length minus 1. There's an edge between a of I and aj if and only if the two share a common factor. Now, what does common factor mean? Essentially, what that means is they are divisible by a prime number. So say that we have the numbers 4 and 6. We can see that 4 is going to be divisible by 2, and 6 will be divisible by 2 and 3. They share 1, too, so these two would be in the same group, let's say. Now 15 shares only 3 and 5, but that shares it with 6, which 6 shares 2 with 4. So these are all be considered into the same group. So this clearly means there's kind of a, what do you want to call it, a relationship by proxy. So if A and B have a relationship and B and C have a relationship, in this case A and C also share that relationship. They're inside the same group. And that's kind of known as a disjoint set union. Alright, so this is not an easy problem. In fact, I will fully admit I had to look up the answer, and even then I had trouble understanding how to solve this. So I think it's best to go through this in steps. Let's first start with how could we find the common factor between numbers. So I'm going to try something different here and just use a piece of pen and paper. Let's start with just a simple example. Consider like the numbers 6 and 12. Now, what numbers are divisible for 6? We already said, right? It's going to be like 2 and 3. What about 12? Well, you could argue that it's got 2, 3, and 6. But there's something funny here in that 6 is kind of irrelevant. It's not a prime number. If it's divisible by 6, we could assume that 2 and 3 are also the case, since 6 has the prime numbers 2 and 3 in it. So all this kind of becomes irrelevant. So the only ones we care about are actual prime numbers, right? So that's point number one. It's divisible by prime numbers. So let's first start with seeing how we could write a function to help us with that. Now what I'm going to do is write a function. We'll call it, well, let's call it primes. And what we're going to do is input a number, any number of some sort, and we want to return a set of all divisible prime numbers. So how can we do that? Well, we know that we want numbers only from 2 and greater, right? Common factor greater than 1. So 1 is irrelevant. Only 2 and greater. So for I in range of 2, we would think n. Well, in fact, it'd be n plus 1. But keep in mind, we only care about prime numbers. So there's a mathematical reason that we don't actually need to go through the whole thing. What we can do is actually just find the square root of this number and add that by 1. So what I'll do is do an int. We'll exponent by, find the square root of that, and we'll just add 1 to that number. Now, what we're going to do here is every time we find something divisible, we're going to do a recursive call and call the prime function with whatever we've been able to subtract as far as the divisible number goes, and see what else is divisible, and kind of add to that set in our loop. So if, let's say, our I, should I say I? No, I should say n is modular n equals 0, that means it's divisible, then what do we want to do? We want to essentially return a set with a list of this current number and union that, or I should say I, I'm sorry, I, and we're going to union by whatever we can return with the recursive call for primes, but now we're going to pass in the n divided by I. If nothing gets through, then we just return the set for our current number, because this essentially means it's prime. So we just return our n. So that's how we're going to find all our prime components for each number. So let's test that out just real quick. We're just going to go for all the numbers in A. Let's print out the self.primes of n. And let's just see what that looks like. Now our test case was something like this, 4, 6, 15, 35. And these are all numbers. So it looks right? It's like 2 is the only prime number divisible for 4, 2 and 3 for 6, 3 and 5, 5 and 7 for 35. So this is going to be key in figuring out how we can find our common relationship between these numbers. Okay, so now what? Okay, that's fine. We have our prime little function here, but what are we going to do to what data structure are we going to use to represent this relationship between all the index numbers? So there's something called a disjoint set union, right? We'll just shorten that to DSU. And I'm only going to go high level here because even I don't fully understand how this works. But let's just say we had some sort of representation that's going to represent all the index numbers for our array. So all these represent the index numbers, and say that these numbers were like, I don't know, actually it was like 2, 4, 6, 9, 49, something like that. Now, if we were to, all these right now are currently separated sets, right? But let's just say we said, okay, 0 and 1, we want these to be part of the common set, because we can see that 4 and 2, they share the same common prime number, so these should be the same. So how can we represent that? Well, we could just represent that by this number equaling the index number itself. So 0 equals 0 here, 1 equals 1, 2 equals 2. So all these are separate sets, right? But let's just say we want these to be joined together. So we'll say 1, hey, now you're going to be represented by 0. Everything else still the same. Now these two are considered one set. This is considered a union. When we do a find, what we're trying to do is find the, like we enter an index number and we try to find the one that is represented, the number represents its position in this index. So all of these currently are. This one would not be. So if we selected 1, it'd say, hey, this is 0. So try looking at 0 and we'll find that, okay, this representative, this is the main one. So this kind of 0 represents our set here. And the same thing could be, occur for here. We can say, well, hey, change that to 2, union these, and this would be like 0, 0, 2, 2. And now these two are 2 sets, and they're non-overlapping, right? So that kind of gives you an idea of what we can do to, we can use this structure here to find how many index numbers are represented inside of each set. So say like for our example here, what we find, okay, we'll forget that for a second. Let's just say we had our prime numbers. We indicated, okay, for 2, index numbers 0, 1, 2 are all inside for prime number 2. Now what about for prime number 3? Well, we have 2, 3, and that's it. And then what about prime number 7? Well, that would be just 4, right? So now these are the prime numbers, 2, 3, 7. Here are all the index numbers represented for the components. And we can just go through all of them and start merging them together. So we can see that 2 and 2 overlap, right? So merge that together. Now we're going to have this number 0, 1, 2, 3. 7, it doesn't overlap with anything, so that's still by itself. So here the max number is going to be 4, right? 1, 2, 3, 4. So I hope that kind of gives you the high level of what is going on here. But coding this out, understanding that conceptually and coding this out is a completely different beast. It's a lot harder. So let's try to get this down. I know I'm going to make mistakes here, but let's see what we can do. Let's first initialize our disjoint set union. And we'll just call that P, and this is just going to be a list of range of, well, let's pass in a number here. So we'll say n, and this is going to be the range of n, a list. And at first, it's going to just be represented by like 0, 1, 2, 3, 4, whatever, right? But now we want to do a find. This will have to say, let's pass in a, like an x number. And we'll say if self.p of x does not equal x, it's not its own representative, then what do we want to do? Well, we want to recursively call whatever this is represented by. So we'll say, hey, continue on upward, see what else we can find. Oops, p of x, like this. And this will be kind of a recursive way, and it's only once we've found that this is true, we can return it. We can say, okay, return the self.px. All right, now union. How do we union? Well, we're going to input two numbers, right? The x and whatever y. So what we can do here is do a find function for both of them. We'll say x1, y2 will equal self.find x and self.find y. And all we'll do now is say, okay, well, p of x1 then, make that equal to y2, whatever that is. And we can actually flip that around, it doesn't really matter, but we'll just do that for now for simplicity sakes. Okay, so now we have our disjoint set union, and I hope I coded that right. Now we got to get to the main meat of our problem. So there's 3 steps here. First, we need to create some sort of lookup hash for all our primes, right? And we can use our prime function to help with that. In our second step, we will I guess unionize, like we'll use our disjoint set union to union all the common elements in each prime set. And finally, we want to return the max number, or I should say max count, within all the what? Well, I guess the representative numbers in our DSU. All right, so let's first create our primes hash, and what I'll do is I'll make that a default dict with a list as all of the values, because obviously they can have more than one index. And we'll say for let's see, for I guess n in A, we're going to create our prime set. We'll say prime set is equal to self dot, do I need self? I think I do actually. Self dot primes n, and for all these numbers, they are going to be index numbers. We are not, wait, hold on. For n in A, sorry, I'm confusing myself here. I'm going to find all the primes, and we will, yeah, we actually need the index numbers here. All right, not a problem. Let's get the index number, and we'll just enumerate. And we'll find all the primes, and for each prime in our prime set, we want to append to our prime dictionary the p, and append what? The index number, right? We want to append our index number for each of the primes that we derive from this number. So now at this point, after it's finished, we should have like a dictionary with, let's say, 2, 3 as our prime numbers, and like whatever list of index numbers that contain this prime number. All right. Okay. So there, we got step 1 finished. Now to create our disjoint set union. So what I'll do, I'll just call that a DSU and call in the, well, let's get the length of our number, and that's just going to be length of A. We'll pass that in with an N. And now at first it's just going to be represented by 0, 1, 2, 3, 4, whatever, right? But here's the thing. We want to go through our prime dictionary or our lookup and start unioning these things all up. So let's see. For we just need the really we just need the values, right? But we'll just say, all right, these indexes in prime dot items. What are we going to do? Let's see. For, I guess, I in range of length of indexes, we want to union these. So we'll say, all right, DSU union. What are we going to pass in? The indexes I, which would be the index inside of this range. So it's going to be whatever index number we're representing from the original A. And we want to union that with what? The next, like, how about the next one? We can just make sure that all of them are unioned by just going, through one pass. And we just say I plus 1. And to get that to work, we'll actually need to subtract 1 here. So at this point, everything that shares a connection should be getting joined up together with the same representative index in our DSU. So if they share a group, they'll now all share the same index number. All right, so at this point, we have our object. That should look good. Now, all we got to do is figure out how many are inside of each group, right? So we could use our DSU find to get the representative number and just say for I in what range of all our numbers and I should say what DSU find I in range of n. Yeah, because all of them will be represented by something between 0 and the range of n. And just, I guess we could return this as a list and use a counter object to say, hey, which one has the most? So just get the values, because we don't care which group it actually is. We just care about what's the largest number, right? So this is going to return to us a list of all the values, and we can just say, hey, return the max of it. And that would be it. Now we just return the maximum count in our DSU. So I hope that is explaining it reasonably well. Of course, I made some syntax errors here. Line 38. Of course, I need some parentheses for this counter. Okay, self.find is not. What? DSU. Let's see. DSU find for I in range. Name find. Oh, okay. So little errors here and there. Self. Okay, so I think that's working. Let's go ahead and submit this. And God, I hope that works. It did. Accepted. Okay, so what a way to finish the month's challenge. They give us a pretty difficult one. I'm going to be straight out and say I did not know this to begin with. And I looked up answers and tried to understand it. And even now, it's still a pretty difficult one. So I think one day I might go into explaining disjoint sets more, because I have seen them before. Originally, I've seen them more to do like cycle detection and stuff, but this was another interesting way that it could be used. So hope that really helps. Really, I'm sure there are better answers, better, more efficient solutions, but I think this will have to do for today. And thanks for your patience. Really, really appreciate it. And I hope this helped. So thanks for watching my channel. And remember, do not trust me. I know nothing.